Good morning, good afternoon, everyone. My name is Michael Kriek, Marketing Communication Manager at DSM Engineering Materials. I'll be your moderator for today's webinar on fatigue life prediction of plastics. Before I give the word to our presenter of today, I'd like to remind you this is a live webinar and we will be hosting a Q&A at the end. So feel free to submit your questions via the questions panel on the right-hand side of your screen. Or if you're following us via the GoToWebinar app, just click the question mark icon and submit your questions over there. And I'll give the floor to Mark for today's presentation.
Okay, thank you, Michael. Thank you for the introduction. And thank you everyone for joining. Indeed, my name is Mark Antos and I have the honor of entertaining you for, let's say, the next 20-25 minutes while discussing our approach to predict fatigue life of engineering plastics. The work that I will be presenting is not just done by myself, but in close collaboration with my colleague Lucia Douven. So as might be of interest to you is where I only have 25 minutes or so today. Lucia will discuss the same topic tomorrow on the DSM Advanced Materials Forum. So in case you're interested in perhaps hearing the story again, but perhaps with more details and a bit different pace, please feel free to also join, let's say, the material science track tomorrow afternoon between 12 and 1 p.m. where Lucia will then take the honor of talking you through the framework in a bit more detail. The outline of the presentation for today is that I will first start with an introduction and also providing you with a motivation why actually a material supplier is bothering doing this kind of work. But after that, I will try to show you some details on the fatigue framework that we developed to predict the fatigue lifetime of short fiber reinforced plastics. So that involves some details on material characterization, that involves some highlights of the material model that we use incorporated in DIGIMAT. Eventually, we also need to correct for stress gradients, so that I will demonstrate how we do that, and I will illustrate the issue that the force ratio is not necessarily equal to the stress ratio. And then eventually we will demonstrate this entire framework on a validation case, and I will also discuss some recent improvements. The nice thing is that this entire framework was now also implemented in this commercial DIGIMAT software. So there was a collaboration project between DSM and E-XSTREAM, eventually on implementing this workflow that also allows you as a customer to eventually use the learnings and insights that we have and perform structural simulations yourself. And then after that, I will of course conclude and provide you with some outlook, and then there's some room for questions. So first, introduction. For those of you who don't know DSM Engineering Materials, or formerly known as Engineering Plastics, we are one of the key material suppliers in automotive and electronics. And we dare to say so because I think you can find our materials in 87% of all cars. And the reason why you can find our materials in so many of these vehicles is simply because we have a very broad portfolio with a lot of different materials that are suitable for different applications. So if you look on the right, we have this typical pyramid of polymers. On the left, you can see the amorphous polymers. On the right, the semi-crystalline one. If you go from bottom to top, you go from the typical commodity from mid-range to eventually high-performance plastics. You can see that DSM has a very broad portfolio of different materials, all based on different semi-crystalline matrices. And therefore, you can also see our materials coming back in a variety of applications in these cars. The one that I'm discussing now, so let's say for today, are mainly these high-performance plastics that you can imagine that are applied in, let's say, the more demanding or the more load-bearing applications in these cars. And that also brings me to the motivation of this work. Because you can imagine that a lot of the market trends are replacing metal by plastic. That is mainly driven by, let's say, this continuous drive for lighter vehicles. And here we use the motivation of, let's say, the reduction of CO2 emissions that is forced by, in this case, European legislation. So as you can see over here, we have the CO2 emission target plotted over the different years. You can see that the emission target was continuously reducing over the years, and the target for, let's say, this year is even more ambitious than the reduction that already was achieved for 2050. And you can imagine that you can reduce these emissions by making your car more efficient or improving, let's say, the combustion process. But a fairly easy trick is also to reduce weight, then you also reduce the emission. When you're going to reduce weight, then you can typically think of replacing the typically heavy part that are made of metal by plastics. And if you do so, you usually start with, let's say, simple parts where strength and stiffness usually suffice. So think of covers and heat shields. But once all of these are already replaced, then you also have to move towards, let's say, more demanding parts to still achieve weight reduction. And then you can think of, let's say, thermal management modules or powertrain components, or perhaps even body and chassis. And with this increasing part complexity, you can also imagine that also the loads are becoming more demanding, and therefore also the significance of durability increases. So in order to be successful in these kind of applications, these demanding load-bearing applications, you also need to be able to do proper computations and proper part design. And that's where also DSM said, okay, we need to make a step up here, because we would like to help our customers in being able to make more reliable predictions and better design approaches. And that's why we said, okay, we want to invest time and R&D efforts in improving, let's say, the fatigue predictability of this class of materials, and also building a tool that is enabled for our customers. So that brings me to an introduction in myself. So as you probably knows, my name is Maurits Kanters. I work at the corporate R&D department. So these kind of, let's say, longer term R&D activities are usually executed at the corporate R&D department for the materials cluster, which is called the DSM Materials Science Center, and is based in Geleen, so the south of the Netherlands. Prior to joining DSM, I obtained a PhD in mechanical engineering for the Eindhoven University of Technology, and I have expertise in polymer mechanics and lifetime prediction of thermoplastic composite materials. I have mainly an experimental background, and that's why we also teamed up with Luchet, who has a strong simulation background, and I think that we were complementary in developing this framework. So now to the fun part. So let's say the content. Let's look at the framework that we developed. So schematically speaking, it looks like this. So if you have the fatigue framework for fatigue predictions, then you can imagine that you have to start with some fatigue data. So you have to capture the R value dependency and the influence of anisotropy. But if you have the fatigue data, you have to convert this into a material model. And here we use the DIGIMAT fatigue material model that basically calibrates your material strength in different directions to predict also the anisotropic performance. To do so, you need to have some information on the microstructure. So you do CT experiments to also measure the glass fiber orientation that you can use as an input for the DIGIMAT material model. The nice thing is, if you know what the microstructure is that resulted from some kind of injection molding process, you can also use that to tailor, let's say, the properties of your flow simulation to also enable better fiber orientation predictions when performing, let's say, a mold flow simulation on your part. And once you know the orientation in your part and you have the material model, you can compute the stresses in a part. If you have the part prediction, then what you will find out is that especially in highly stressed regions, you'll find that there's an effect of stress concentrations which you have to correct. So this notch sensitivity has to be calibrated and also taken into account, as we will demonstrate in a second. So I will try to do step by step, highlighting some of these parts. The flow simulation I will skip. In case you want to hear more about that, you can join the call from Luchet tomorrow or ask me and contact me after this call. But I will try to give you a glance of all these ingredients in the fatigue framework. So first, the fatigue data. Well, what we want to do is we want to build up a certain validation sequence. So instead of just measuring, let's say, the R value dependency and anisotropy and then trying to do a part prediction, we want to really understand where we do well and where we do wrong. So that means that we actually want to validate against a series of specimens while we gradually increase complexity in geometry, loading conditions, and fiber orientation. So you can imagine that we start with a typical standard injection molded tensile bar, so highly oriented fibers. We also move to samples that we mill from a plaque. So from an injection molded plaque, we take tensile bars from the different angles. And instead of just using the minimal of 3 that is usually used for calibration, we also studied, let's say, other angles, let's say 15 and 30 degrees, to see how well can we predict the influence of anisotropy. Then from the same plaque, we also mill tensile bars, in which we introduce a certain notch. And instead of just only introducing various notch radii, we are also able to vary the fiber orientation combined with the notch radius. So with that, we introduce a different stress state that we can again study whether we can predict, let's say, the fatigue life of such an intermediate part with a slightly more complex stress state. The same thing holds when we cut beams from these plates that we use for 3-point bending. Then we again introduce a different stress state that we can again study as function of fiber orientation. So with this, we can build and also validate our fatigue framework. And eventually, we want to validate this or compare this with a prediction on what we call a representative real part. So we had in-house development of a demonstration part that we can also load in fatigue. And the demonstration that I will show today is on the load bracket. And if you look at the typical results, I think what we do differently is that we actually recognize the fact that you have multiple failure mechanisms. So some of you might be aware of if you plot the SN curves, so the stress versus the lifetime, then you might see two different regions. So you have one region which is persistently controlled and one region which is backward controlled at longer times and lower number of cycles. But if you then play around with amplitude, which is captured by this so-called R value, so the minimum load divided by the maximum load, you can imagine if this R value is equal to 1, you just have a static load since both loads are equal. And if this R value is decreasing, you gradually increase the load amplitude. But if you do so and you look at the fatigue performance, then you see something nice appearing. Because for this persistently controlled region, you see an increase in lifetime with decreasing R value or increasing amplitude. And at longer lifetimes and lower loads, you see the steeper region actually shifting towards lower lifetime. So you see that for the backward controlled failure, lifetime decreases with increasing amplitude or decreasing R value. So that's a bit counterintuitive, but the fact is that if you recognize that these two mechanisms are there, you can also proper model these. So that means if you have proper understanding of both failure mechanisms, then you can also better predict failure at any arbitrary load ratio. And to demonstrate this, you can see here now the fatigue data that we measured on this polyamide 66 50% glass fiber. You can see the maximum load versus the number of cycles, so the typical Euler curves of the SN graphs, for RS -2 ranging up to RS1. So let's say creep rupture up to a very large tension compression load. And then if we compare our models calibrated on these data points, then you can see by plotting these that you indeed see that our models describe the experimental data points very well. Logical, because we also use these to calibrate a material model. But the advantage of having this based on a model is that we now can predict the performance at any arbitrary R value without measuring it. So we can also interpolate and extrapolate and predict the load ratio dependency of each failure mechanism properly. And this is here illustrated on the right with the so-called Goodman diagram, where they plot the mean stress versus the stress amplitude that allows you to give some direction when you have variable R value, variety of R values of your part. So this was a glance at how we treat, let's say, our fatigue data. You can imagine that now I demonstrated this for R value dependency, but we also do something similar for anisotropy. We studied both the influence of glass fiber orientation and R value for that. And these details we can now feed into a material model. So first, before we can go to the material model, you have to understand what the microstructure of this plaque looks like. Because since this plaque is ejection molded, you can see initially you already have some kind of biaxial stretching in the beginning. And in the end, you have the shear flow because of filling the remainder of the plaque. So as a result, you can imagine that at the edges, you have highly oriented fibers because of this flow. And in the middle, you have more or less perpendicular oriented fibers to the flow because of the biaxial stretching. As a result, you get a very pronounced glass fiber orientation, as you can see over here on the left. So you plot the A values, so basically the values of the orientation tensor, or A11 is the orientation in the flow direction, A22 the orientation perpendicular to the flow direction, and A33 the orientation out of plane. Then you can see that in the 2D plane, so basically in the plane of the plate, you have a very pronounced skin core morphology because of the edges. So let's say on the outside, you see that you have highly oriented fibers, and in the middle you have perpendicularly oriented fibers, and of course it's symmetric because you have the edges on the other side. So you have to take this into account because as a result of this, let's say pronounced gel core structure or skin core structure, you also get a very anisotropic material behavior. So here on the left, on the right, you can see the true stress versus the true strain. And you can see that looking at the 0-degree performance and 90-degree performance, that the loading direction really matters on how the material performs. On this stress strain data, you can fit, let's say, linear elastic material properties. So all the fatigue simulations are done using a linear elastic material model, as I'll demonstrate in a second. So we capture, let's say, the orthotropic material properties using these stress strain curves. And then eventually we fit, using the stresses that we compute on that, on the tensile bars, we fit, let's say, the failure indicators, which are the strength directions in either the in-plane direction perpendicular or let's say the shear direction. If you do that properly and you compare, let's say, the DIGIMAT material model prediction, or let's say the calibration for anisotropy and R value, then we typically use these plots. So on the x-axis you have the measured number of cycles, on the y-axis you have the predicted number of cycles, and then you can see if you have a perfect match, you match this thick gray line in the middle, because that means that your measure and prediction are exactly equal. If you have this thinner gray line, that means that you're a factor 3 off, and this dashed line means that you're a factor 10 off. Then you can see that for different R values, highlighted with different type of markers, and for different orientations, highlighted by all the different colors, we can describe our entire data set well within this factor 3. So that means that we have a material model that can capture the influence of anisotropy plus R value very accurately for all the data that we have measured and used for these input calibration curves. So hopefully that gave you some idea about the DIGIMAT material model that is used, and also about the microstructure that you see and the influence of that. The next would be is now to zoom in on the stress concentration correction. Because as you might know, is that if you do a finite element calculation, so this is a calculation on the notch bar. This is 1/8 of the notch bar. So you have a symmetry axis here, a symmetry axis on this plane, and a symmetry axis here on the back. And if you do this on this double-edged notched bar, you will always find a huge stress concentration or a huge stress amplification behind the notch. And you can see also here that the stresses at the edges are higher because of the shell course type of structure. But it gives a problem, because if you use that local extremely high stress to also compute your lifetime, then you will always underestimate the lifetime of your part. And that is illustrated here in the middle. So here on the y-axis you have maximum force plotted versus the number of cycles to failure. And you can see the markers here are measurements, and a dashed line is, let's say, the initial prediction when you just use this local high maximum stresses. So it's not very good actually. But this is something which is known, and that's why we decided, okay, let's just do the things that they also use when they try to predict fatigue for metals, and that is to correct for, let's say, these fatigue notches. So you can use a support factor or the fatigue notch factor to compute an effective load by scaling down the maximum local stress. And we decided to use the theory of critical distances, which uses the normalized stress gradient. So how fast does the stress Tk on a path perpendicular to the maximum principal stress? And with this normalized gradient and a characteristic length, you can more or less define how severe this local stress concentration is. And to calibrate that model, the only thing that you need to do is you need to find a certain Kf value, and you need to compute a certain normalized stress gradient, and then you can fit a certain characteristic length. And in practice, it looks like this, because first you underestimate, but you have measurements. That means you can manually shift your curve through your data points. You can see that we try to focus on the high number of cycles, and we are underestimating the local, let's say, lower number of cycles. But I will come back to that in a second, because this has to do with plasticity that we can also solve. But we decided to focus always with this calibration on, let's say, the higher number of cycles. But by scaling this, you compute a certain Kf value, and since you have a certain geometry, you end up with a certain normalized stress gradient. And you can plot those two against each other, as is done here on the right, where you have the fatigue notch factor versus the normalized stress gradient. We did this for a lot of different orientations and a lot of different notch radii. So of course, with a sharper radius, you increase the normalized stress gradient, and every different color represents a different orientation. And with that, we can fit this theory of critical distances. So we just calibrate a certain characteristic length. And as you can see over here, with a constant single characteristic length for all orientations, we seem to describe this trend reasonably well over this entire range of normalized stress gradients. So we decided, okay, it's practical to just stick to a single characteristic length. And with that, we can also achieve reasonable model predictions. So the blue curve is the one corrected using Kf. And then the markers are, again, the experiments. But one consequence, of course, is we are scaling our local load. You all might appreciate that, let's say, the lifetime is very sensitive to stress. That means that actually we have to take into account that this plus minus 15% is actually also plus minus a factor 5 in life that we introduce. But nevertheless, with that framework, as you can see over here, again, the measured versus predicted lifetime describes, let's say, the lifetime for a huge range of notch radii and a lot of different orientations very well. So introduce a bit more error, but again, we can describe the lifetime of notch specimens reasonably accurately. So now I hope I also tackled a bit of the stress concentration. The flow simulation I can unfortunately not tackle today in view of time. So next thing will be the part prediction. Because as I mentioned, we are eventually validating our prediction next to this demonstration later part. So here you can see a movie where we load this part on fatigue, and that means that we apply a certain R value and force. It ranges from the minimum force divided by the maximum. I try to go for a large range of force R values, ranging from 0.5 to -2, and then we end up with these kind of SN curves. So you have the maximum force plus the first cycles to failure. The nice thing is, as you might see from this part, that it's asymmetric. So you can imagine if you push with a certain force or you pull with a certain force, that you get some kind of localization of the failure location. So if you go to RS -2, which means that you push twice as hard than that you pull in the maximum load, then you see a failure location here on the bottom. But for all the other ones, where actually the R value is bigger than -1, that means that you pull harder than that you push, then you always see failure on the top. And this was also correctly identified by the framework. Then the next thing what you can do is, besides looking at the failure locations, looking at the stress levels. And if you do so, and you do it, let's say a load of 1500 newtons, if you push with 1500 newtons, you end up with a compressive load here on the top of -34.3 MPa. But if you then look at the stress levels in the same region, but then when you pull with 1500 newtons, then you can see that the load is much higher. So it's 94.3, partly due to this anisotropy and partly due to the fact that you have boundary conditions because of washers that are applied while applying the bolts. So that means that we apply a certain force ratio which is equal to 1, but the local stress ratio is far away from -1. It's actually only 0.4. So that means that you really have to take into account the local stress ratio to do properly fatigue calculations, simply because the local R value is really affecting the lifetime of that response. And this is once more highlighted here on the right, where you then plot the R value versus the maximum applied load, and then for different R values, but this is black one as example for RS -1. You see that we think that we apply RS -1, when in reality the R values are somewhere between slightly above 0 up to -0.5. So you really have to take this into account. The deviations can be really big, depending on the geometry. But if you do this properly, then we end up with a certain part prediction, as you can see here on in the middle, where we again plot the measured lifetime versus the predicted lifetime for all these different R values. And what you can see is we were a bit disappointed. We are underestimating somewhere between a factor 5 to a factor 30 for most R values. But what you might appreciate is that although the lifetime is drastically affected by the R value, we seem to properly capture this because everything is located in the same cloud. And besides from that, you can also see that the lines here are parallel to, let's say, these gray lines. It also suggests that the force dependency, which is again also affecting the local R value, is also captured well. So although we wanted to do a bit better, we were already quite satisfied with this result after analyzing it properly. So in conclusion, we can capture the failure location, and we are slightly conservative, but we can already predict within a factor 5 to 30 accurate, and we can properly capture the R value. So I hope that it also gave you a glance at, let's say, the part prediction capabilities. Next step would be then also to discuss some recent improvements. Because you might already have noticed that I mentioned that we do linear elastic computations. So especially at these high local stresses, you will start overestimating the performance because you will follow this red line where in reality the material will yield and follow this elastic plastic performance. This can be solved because you can correct for that by, for example, using the Glinka correction, very similar to the Neuber correction, as you might be aware of, where you just use the elastic free energy density and you look for the equivalent one in elastic plastic range to knock down your local stress levels. And this brings us to the advantage of using DIGIMAT, because the colleagues from DIGIMAT are very good at predicting, like say, the elastoplastic material performance for a lot of different fiber orientations. And they can do it so efficiently that they have a hybrid option to just only do this for, let's say, the elements that exceed a certain yield stress. And with those image input, we compute the plastic stress field and also compute the new local R. So to give you a glance at this, is that what then happens is that I already demonstrated this, where we compute KF and underestimate the initial local stresses. And therefore, we also see deviations, let's say, at the lower cycles where you start to underestimate the performance. But simply by just applying the plasticity correction, but just applying an elastoplastic material model, we are already immediately spot on also for these kind of local stresses without any recalibration, just giving it some kind of yielding, and then also the entire performance also improves, as you can see over here. So the change in slope is actually accounted for by plasticity correction on coupon level. And the nice thing is that if you then also do this on parts, then where the initial prediction was between this factor 5 to 30, actually locally this high local stress already results in yielding. So if you then compare it with the new prediction with plasticity correction, you can see that all these points shift into this factor 3 type of range. So the predictions of these complex parts are well within this decade. So we're really happy of seeing this. And it also tells you that if you combine a plasticity controlled failure with aggressive circulating correction, that you really achieve targeted results, which we set up between a factor 10. And the nice thing is that this approach using the gradient and plasticity is also robust to mesh size. So here you can see the results for 3 different mesh sizes, and being all consistent in all cases, which is also convenient. So it doesn't mean that you have to recalibrate the model when you start changing the mesh density. The reason why it might be of interest to you that we had a collaboration is that E-XSTREAM, so the company behind DIGIMAT, also implemented this workflow. So we had a goal to implement this to have more, to enable you to do more accurate fatigue lifetime prediction at part level, to simply enable our customers using our material cards. And it's ready and available from DIGIMAT 2019.1, so even including the plasticity correction. And that means that you have an RP, a post-processing tool to compute your local lifetimes. And we also supply 2 different material cards, and polyamide 66 and PPA, both with 50% glass fiber, that are now available, albeit on request, to perform structural analyses. And that brings me to conclusion and outlook. So I hope that I showed you in this probably high speed that for accurate prediction of fatigue life of short fiber reinforced polymers, you need to look at the local load ratio. You need to take into account glass fiber orientation, local plasticity, stress gradients, and the fiber orientation distribution. But if you do this step by step, you end up within that 1 decade accurate. And we have some further steps, but with that I would like to conclude. So in case you want some references, we published a majority of this work on 2 different papers. But please reach out if you want to know more. Please be aware of, let's say, the time slot for tomorrow for my colleague. We'll present this in more detail and probably a bit lower pace. Thank you for your attention. And are there any questions?
Yeah, thanks, Mark, for your presentation. We're now opening up for questions indeed, so feel free to submit your question via the questions panel on the right-hand side of your screen. We have a couple of minutes to answer your questions. First question here, Mark. All the results presented here are at room temperature and dry as molded. What is your view on extending it to higher temperatures and humidity?
Okay, thank you for the question. Actually, that is what we're working on now this year. So I more or less left it out on the outlook. But actually, we are working on an approach to validate mainly the R-value dependency and implement the anisotropy also at different temperatures. And especially, we are looking for tricks to efficiently characterize notch sensitivity, because we just demonstrated a lot of experiments and a lot of details to calibrate the material model. And we now want to narrow this down to, let's say, lesser number and more efficient calibration that also allows us to properly study the influence of temperature and relative humidity. So hopefully we can share more on that, let's say, within half a year or so.
Okay, thanks. Next question here. You demonstrated many features that need to be taken into account for proper lifetime predictions. Which of these are leading to the most significant improvements?
Thanks again. So you can see here this list of the different features: so local load ratio, fiber orientation, plasticity, stress gradient, and orientation distribution. But I think in all fairness, I think where we really make it step up is predicting this load ratio dependency, because it was really important to get the prediction on part level well. And also this local plasticity combined with stress gradient is really key to make a consistent bottom-up approach to predict a lot of different geometries and eventually also end up with predictability on part level. So I would say the local load ratio is key, local plasticity and gradients. And for graph fiber orientation, we just use the state of the art, but I think that is not that much improved by our efforts.
Okay. Another question here, do your models only apply to in-plane fatigue, or could it address out-of-plane stresses details as well?
Yeah, at this moment we only look at in-plane, that's correct. But actually for the part, you'll also look at multi-axiality. So you look at the max principle, that is the main driver for, let's say, the gradient correction. But besides from that, the failure indicators are computed using the multi-axial stresses. So actually it can also look for out-of-plane stresses and take those into account. I think the strength of this calibration of the anisotropy material model.
Okay, thanks. Another question here. In applications, the frequencies can be very high, for example, caused by vibrations, and the loading conditions are seldom with a constant amplitude. Does this work still apply for those cases, and if so, how?
Yeah, that's usually a challenging one, because the problem is if you would test on material characterization at these high frequencies, is that you usually end up with too much heating. So that means that, let's say, the material performance that you characterize is not representative for let's say, isothermal behavior, but it's simply affected by how much heat you generate because of the cyclic load that you apply. So that's why we really focus on generating isothermal fatigue curves that allow us to with confidence extrapolate to also higher number of cycles that are more relevant for, let's say, the high cycle fatigue and, for example, resonance mode. The only problem is, of course, you would like to validate these kind of things, but as far as we know now, studying the frequency dependencies, is that with characterizing at low frequencies isothermal behavior, we are also able to extrapolate to use also for higher frequencies and lower load levels very well.
Okay, thanks. Next question here. Is local R ratio changing? Do you use a cyclic stress strain curve?
Yeah, we do not use a cyclic stress strain curve. So we were really surprised that, let's say, the elastoplastic behavior, so let's say the quasi-static stress strain curve was sufficient to correct for this nonlinearity. But in all fairness, although it's different a bit on frequency or cyclic load, it's not that different from the quasi-static load. And the R value dependency, as we can show on this graph on the right, because of the asymmetry in the geometry, it evolves as function of applied load. So it does not evolve as function of time, because we don't update on our stress strain curve or stress strain behavior, but it does change with applied load level. But you don't have any stiffness reduction or damage accumulation in the calculation included.
Okay, well, no more questions, so I suggest we conclude this webinar. Thank you very much, Mark, for your interesting presentation. As you also mentioned, tomorrow we are organizing the Advanced Materials Forum. It's a full day online forum with many different interesting speakers and sessions. It's free, so make sure you register and get access to all the sessions. There will be a link in the email that you will receive after this webinar has finished. We're also organizing more mini webinars like these in the coming days, so also look for other interesting topics in your email. And with that, I'd like to thank you, Mark, and thank you participants for joining this webinar, and hope to see you soon.
Yeah, thank you everyone for attending.